You probably know that computers don't understand human language, but only zeros and ones, which means binary. But does this even make sense? I mean, you can't make silly GIFs with just zeros and ones, right? In this video, I'll explore computers from the absolute basics to understand how these pieces of metal, wire, and plastic carry out complex tasks, or even simple logic like addition. And relax. You don't need any prior computer knowledge at all. Here I have a simple circuit with two switches and an LED. The LED glows only when both switches are closed, otherwise it stays off. We'll represent an off switch as 0 and an on switch as 1. This gives us a table where the output shows if the LED is glowing. It only glows when both switches are 1. This is called a truth table. Since it needs switch A and switch B to be closed, we call this the AND operation. Now, here's a different circuit where the LED glows even when the switch is open. As soon as I close it, the LED turns off because we've created an easier path for the current to flow. The current will travel the easier path. We are basically getting the opposite of the input. If input A is 1, output is 0. If input A is 0, output is 1. This is the NOT operation. I was controlling these switches by hand, which computers can't do. Originally, they used clunky electromagnets, then vacuum tubes, and finally transistors. To understand transistors, I've set up a NOT operation on this breadboard, using a transistor instead of a paperclip switch. Right now, it acts as an open switch, blocking current, but when I apply power to the middle pin, it lets current flow through, taking the easier path. So, transistors are just switches controlled by electricity instead of hands. I'd love to build a whole computer from these tiny parts like JDH, but for now, that's a bit hard. Here is a small simulation like the one Subastian Lauage made. I have two inputs and one output. If I connect them through an AND gate, it works exactly like the circuit we saw. The output glows only when both inputs are on. Now, let's use a NOT gate. I'll connect the AND gate's output to the NOT gate's input, then to the main output. Now we see a different behavior. The output is off only when both inputs are on. This is called NOT AND or NAND. I'll turn this into a new chip. We can build many operations with this. If I invert both inputs before they enter the NAND gate, the output stays on if either input A or B is on. This is known as the OR operation. I'll pack this into its own chip too because it seems very useful. Now, let's talk about something important: numbers. The decimal system we know has 10 digits, 0 to 9. To go higher, we add a digit to the left, where each position is 10 times the previous, ones, tens, hundreds, thousands, and so on. But in electronics, it's easier to work with just two numbers because we can represent them naturally with low and high voltage. This binary system works like decimal, but we run out of digits after 1. Since there are only 2 digits, each place is 2 times the previous. 1, 2, 4, 8, and so on. To convert the binary sequence 1101 to decimal, we calculate 8 times 1 plus 4 times 1 plus 2 times 0 plus 1 times 1, which equals 13. Now, I want a system to add these binary numbers. Let's look at an example. Starting from the right, 1 plus 1 is 2, which is 10 in binary. I'll write 1 as a carry and 0 in the sum. The bottom digits are sum bits and the top are carry bits. For the next digit, 1 plus 1 is 2, plus the carry 1 makes it 3. In binary, 3 is 11, so I write 1 in carry and 1 in sum. Next, 1 plus 1 is 2 again, so carry 1 and sum 0. Finally, 1 plus 0 is 1. I just added 35 and 7 to get 42. Figuring out how to wire logic gates for this isn't easy, so let's start small with 2 single bits. If I add 0 and 0, both sum and carry are 0. If I add 1 and 0, carry is 0 and sum is 1. If I add 1 and 1, carry is 1 and sum is 0. Looking at the carry column, it's exactly like an AND gate. The sum column is similar to an OR gate, but with a 0 at the end. I'll use this OR gate as a starting point here. I just need to turn off the output when both inputs are on. I'll also use a NAND gate here so I can check if both inputs are 1 and then invert the result. Now I'll use this AND gate as well to test that only one of these 2 inputs is 1 and not both. So let's quickly test this. If I set either of the 2 inputs to 1, the output remains 1, but as soon as I set both inputs to 1, the output becomes 0. This operation is called an exclusive OR, or simply an XOR. Now I have an empty chip for adding 2 bits with 2 outputs, sum and carry. I'll use the XOR gate for the sum bit. Since the carry is only 1 when both inputs are 1, I can use an AND gate for that. This works for 2 bits, but sometimes we need to add 3 bits because of the carry from a previous step. I'll add a carry input. I connect one XOR gate to the first 2 bits, then its output to another XOR gate with the carry input to get the final sum. I'll use another AND gate to see if the first addition and the carry input are both 1. Now I have 2 AND gates checking different carry conditions. I'll use an OR gate to see if either condition is met to set the final carry to 1. If all inputs are 0, sum and carry are 0. If one input is 1, sum is 1. If any 2 are 1, carry is 1 and sum is 0. If all 3 are 1, sum and carry are both 1, because 3 in binary is 11. Everything seems to work. I'll call this an adder and use it to build a 4-bit adder to add 2 4-bit numbers. I added displays to show their decimal values. I need 4 adders, connecting each carry out to the next carry in. Finally, I connect the inputs to the numbers. Zero plus 0 is 0, 1 plus 1 is 2, and other numbers work too. There is one exception. If the sum exceeds what 4 bits can represent, like 15 plus 1, it causes an overflow and the carry bit becomes 1. I hope you liked this video and the journey of creating logic from metal pieces. Now, you know how computers work at a low level. I'm planning to expand this series, so stay tuned to the channel. Thanks! See you soon in Computer Science for Actual Humans 101.